This lecture is definitely getting into the kind of stuff that you'll see a lot more of if you take the operating systems class. So pretty fun stuff. What we're going to spend a little bit of time doing is fleshing out the implementation side of our process model, fleshing it out a little bit. We're not going to go into all the gory details, but we started talking about how there's an API that's very simple to use, and we've talked about all of these functions at some rough level now. Fork, exit, wait, PID, exec VE, which we introduced last time. That's how a process starts a program. So Unix has this notion that every process is started by some other process. There's a hierarchy of ancestry, if you will. And if you want to run a new program, well, you have to fork an existing process and then exec VE it to start running a new program in that process. Windows' model is slightly different. So there's no one true model, but it has many similar characteristics. And the implementation we started talking about is much more involved, and we started talking about this state diagram, where before we said that we had running, stopped, and terminated. Those were our three states, but that's not realistic because really we can only have one process running per processor at any given time. So we have other processes that are in the wings, if you will, waiting to get on the processor. So we had this whole ready running interaction. It goes back and forth. A running process can block on some resource that takes a long time, the disk or the network or a human being. And so it would remain in that block state, not being scheduled until the resource becomes available. Then it can go back over to ready. And then suspended represented our stop states, where these processes may or may not be able to execute even if they had the CPU, but we just don't want to schedule them. And then the terminated state is obvious. So we had this state diagram. Did anybody have any questions about it? Nobody had questions last time, but just in case somebody thought of something interesting to ask. So that was basically what we had, and we were talking about how, I've already talked about all of these things. So we have processes in various states. So the kernel has various data structures that it has to manage to keep all of these things straight. And not to put too fine a point on it, but you can imagine that these data structures have to be cache friendly. They have to be friendly to fragmentation issues. We have all kinds of things that we have to keep in mind if we're writing a kernel, because it is the most important piece of software on the computer. It has to be the most efficient. It runs the longest, so it has to be good when it comes to fragmentation and so forth as well. Okay, now we're going to talk about a few of these things. Different operating systems do it different ways. You can take the OS class if you're really curious. But we have this process control block, or some data structure that describes every process on the system. And depending on the OS, we may even have a data structure per thread if we have an operating system that supports multi-threaded processes. But like I said, this process control block is going to contain everything necessary for managing the process, and it's also going to include the context information for the process when it's not actually running. So this would be representative of what you'd see on Unix. So process ID, parent and child process IDs. When it's not running, the context of the process, information about the resources the process is using, particularly if it's stopped, or I shouldn't say if it's stopped, but if it's blocked on some long, or I should say slow resource, then we need to keep track of what resource we're actually waiting for and so forth. Pending resource requests and scheduling information. And you can see that the kernel is basically a big librarian or a big bookkeeper trying to keep track of all these processes. What are they using? What are they waiting for? Who's done what? Who's waiting for the CPU and so forth? So the operating system is actually a very straightforward thing to understand, but it also has a lot of nuances when it comes to concurrency. That's actually probably the number one place where complexity in operating systems comes from. Okay, so process control blocks, you can look at it like this. So we have ID information, state vector, status info, hierarchy, and each one of these sort of captures an aspect of what we just described. So we have process IDs that map to process control blocks. There's several different ways that kernels do this. Linux has a hash table because it makes a lot of sense. You want this mapping to be as fast as possible. If I'm sending a kill signal, and remember, kill just means send a signal. It sounds very dire, but in fact you can send all kinds of signals that don't mean terminate the process. But if I'm sending a signal to another process, I've got the process ID in there, and I trap into the kernel and ask the kernel to do it on my behalf. I need that mapping to occur quickly. So a hash table makes sense. I don't necessarily want something that I have to have a log n lookup, or an order n lookup would be even worse. So we want it to be fast. And there are a limited number of process IDs that may be in flight at any given time. Like there may be a maximum of 64K process IDs on the operating system. And I could have an array of entries where the process ID is just the entry in the array, and I use that to map to the process control block. But the presumption is usually I'm not going to have a huge number of processes. Remember that processes have a weight to them. They have a cost associated with them. And so you don't want to just have as many as you possibly can have, because that's going to make your whole system slow. Context switches are slow. They utilize resources. They utilize memory. So we actually want to have a system where there's not a huge number of processes if we can. So that's why a hash table makes a lot of sense. Now, since we're on Unix, we also have this parent-child relationship, so we have some state for that. This is an example of something that may not be present on Windows because it has a much more sort of peer-based model where you don't really have parent and children as being as important as it is in Unix. But we'd have this information. We have state information, so this is going to capture things like the context of the process. CPU state, so one of the things that's really interesting is like I say here, this is going to include register content, so this is part of the context for the process. But there's also things like if I have multiple processors, I may want to set an affinity to a particular processor. Why might that be? Why might I want to have an affinity to a particular processor? I'll give you a big giant hint. It has to do with caching. Yeah, each processor has a separate cache, and so if I want to have a particular affinity to a specific processor, then what's going to happen? What's going to be likely when I context switch back to that processor? Yeah, ideally, some of that data is actually still going to be in my processor's cache. And so my program won't need to be reloaded from memory. My data won't have to be reloaded. It'll all be right there. So you have this interesting thing that even when you're doing interrupt handling on a multi-core system, the interrupt handlers have to be loaded if they're not in the cache. And so sometimes it makes a lot of sense to make one core on your system take it for everybody else and handle all the interrupts, because that way you have certain benefits, certain performance benefits that you get. Now there's also benefits from round robining that kind of stuff, and so again you can set affinities for that kind of stuff in your programmable interrupt controller. But it's the same thing with programs, and in fact if you get into anything like finance, this kind of trading that goes on, the real-time trading where you try to handle things as quickly as possible, processor affinity is really important because when you need to react as quickly as possible, you want to make sure as much of your information is already in the cache. So setting processor affinity is useful and other things like that. So there's a lot of details that you can set in that CPU state. Okay, so the processor, obviously when you are running, you need to know what processor you're actually on. So you have that information recorded as well. Memory, so that's going to be, this is something that we haven't talked about yet, and I'm excited because next time we'll get to start talking about it. But this is where we actually keep track of the memory state of the program. So this is somehow, right now it's magic. It's either magic or it's horribly slow, and so we'll pretend it's magic. That we have some way of capturing the entire memory state for the process in some reasonably efficient way. And then various resources as well. What files do I have open? What sockets do I have open? Because Unix has this interesting thing. Program A opens a file. Let's just call the file F. Program B comes in and deletes F. What happens to program A? Does anybody know? This has a very specific defined behavior on Unix. Does program A get screwed?
I think it still uses the file.
Okay. Is anybody else allowed to access F after B deletes it?
I think it still accesses the version that it has.
Yeah, so you're on the right track. You've got like 99% of it. So what happens is, remember that there's a difference in the Unix operating or the file system between the directory entries and the data, the file data on the disk. And when you unlink a file, you just remove the directory entry. And the operating system keeps track of how many directory entries refer to file data, and when the number hits 0, it reclaims the space. And so if program A opens the file, and program B comes in and deletes it or unlinks it, then there's no more directory entry for that file, but the operating system still knows that program A is using it. And so the file data itself doesn't get reclaimed until program A shuts down.
But don't you usually get a file in use error when you can remove something?
It depends on what operating system you're on. The way that I described is how Unix does it. Windows is very different. Like you can, and actually you can do this on Unix as well. I haven't talked about it, but it's possible to actually lock a file. So you're saying, hey, I'm using it and I don't want anybody to do crap like that. But in general, if you don't say anything, if you don't use the more advanced APIs for doing this kind of stuff, it'll just allow the file to be deleted, but program A will keep getting to use it until it shuts down, at which point the OS will clean it up. And so you have things like that, resources. The operating system, again, keeps track of what resources are in use, what files are open, blah, blah, blah. And that way it's able to do these kinds of things. Again, operating systems sound very fancy and very amazing, but they're really just glorified bookkeeping software. You know, keeping track of what processors are doing and allowing them to coordinate. Okay. All the complexity comes from concurrency. All right, so enough about that. Let's see, current status. So we have details like, well, what state is the process in? Am I blocked on a resource? If I'm blocked, what am I blocked on? So that when that thing becomes ready, I can then see if my process is able to proceed. Okay, so we have details like that. So running, ready, blocked, so forth. And there may be other states as well, like I'm suspending this process, so I, the user, am suspending it, so I don't want it to actually be scheduled, even if it can run. And this data can be used for a lot of other details. Like you see here, other processes in the same state and priority. We haven't talked about scheduling yet, but we're going to today. We'll start talking about that topic. And so we can have various status details, like how well-behaved or badly behaved a process am I? Do I love computing or do I love doing I/O? Because those kinds of things affect scheduling decisions the operating system might make. Okay, now we have these various operations that we need to support. None of them are terribly complicated, but we're going to look at the pseudocode for all of these. So create, destroy, suspend, and resume. You can see that the argument is going to be a process, except for create, which returns the process that it creates. And of course, there's a detail here that you notice, which is if I destroy the currently running process, or I suspend the currently running process, I need to decide what process gets the CPU next. And so this is where the scheduler comes into the picture. And this scheduler has a really challenging job because it may have 20, 30, 200, 500 processes to choose from, and it needs to make good choices, and it needs to do it fast. And we'll talk about what good choices means in a moment, because we have to sort of figure out, well, do we want the user to be really enraged because every time they type a character it doesn't show up for 3 seconds? Or what do we want to do? We have to make those decisions. But what we can do basically is when we create a process or we suspend a process, depending on why we suspend it, we can go ahead and throw it into the ready queue, and then the scheduler will, again, magically choose the appropriate process to pick and start running next. So that's what the scheduler does. So we'll just talk about invoking the scheduler to say, hey, give me another process to run. Okay, so create, so we need to allocate the process control block or whatever. I'm trying to remember what Linux called it. I should probably not guess. But anyway, it has some data structure, allocates it, initializes the contents, assigns a process ID to it, assigns the mapping so that when I say, hey, here's a process ID, I can get to the process control block and so forth. We need to set up the initial context for the process. Now, obviously, if I'm doing fork, then I just copy the process's context that invoked fork. So that's really simple. I can just copy and paste, which makes it really simple. Something like Windows has a little bit more challenging job because it has to set it up so that it's, whatever program is being invoked, the state is appropriate for that program to be starting at its beginning. Okay. So this is obviously something that Unix factors out into execve. Execve goes in and modifies the CPU state to say, hey, I'm starting this program, sets up the memory state, sets the program counter, the initial program counter to be that 804 8000 so that it can start running and so forth. Okay, so we do all that, initialize resources. In Unix, again, this is very simple. We just copy the invoking, the forking process's resources, and then we have those. If you're on Windows, again, you'd probably say, okay, I need to set up a standard in, a standard out, I need to get those things set up and so forth. And then anything else, we need to set the priority to some default, and we need to set various other things. And once we're done, we just drop that process into the ready queue. Wherever, I don't know, maybe at the back, that would make sense. And then that's it, off we go. The scheduler will eventually schedule it. Now suspend is interesting. Like I say, if the process is currently running, then we need to stop it, and we also need to realize that we're going to switch to another process. But it is possible that we may be stopping a process that's somewhere else. If we are on one CPU and we're stopping a process running on another CPU. And so, like I say, we need to change the status to suspended, which will either correspond to ready suspended if it's from the ready state, or block suspended if it's blocked on some resource. So we have something like this. If the status is currently running, then we have to have a way of stopping it. Then we switch its status to ready suspended. Because, if it was running, then we know it wasn't blocked, right? So we can switch it to ready suspended. Then we invoke the scheduler to pick somebody else to run. And if the status is ready, then we again switch to ready suspended. If it's blocked, then we switch to block suspended. Really easy. But these last two conditions, these last two possibilities, we know that it's not on the CPU, so we don't need to stop it, and we don't need to invoke the scheduler, because we're not replacing a process, or we're not pulling a process off the CPU. Okay, any questions? Stop is a separate function. And there's a reason why. And like I said, we record the entire context into the CPU state. The reason why we like it to be separate is because we do have the possibility that we're on a multi-core system. In fact, almost always now it's the case that we're on a multi-core system. Even freaking cell phones have multiple cores now, which just blows my mind because, like I said, AT, running 4.77 megahertz, single core. I didn't even have a math coprocessor when I started, so it's kind of blows my mind. Anyway, so the thing about stop is, if you have a program running on one CPU and you need to interrupt a program running on the other CPU, what do you fall back on? It's the same thing that we've talked about before. Hardware exceptional flow control. And these programmable interrupt controllers are really neat. This program can actually say, hey, I want to cause an interrupt on this other processor. And so it goes ahead and causes the interrupt to occur, and the kernel gets trapped into, and the kernel says, oh, I'm supposed to do something with this process. So you have this interprocessor interrupt, it's called, that you can invoke to stop a process on another processor. So that's a pretty neat thing. Okay, so like I say, if the computer has multiple processors, the kernel may be executing on one CPU while the process P is running on another processor. Okay, so that may be the one situation. So I need to do an interrupt. If I have a single processor, I'm already in the kernel. Yay. And in fact, the way that kernel traps work is that when you trap into the kernel, it automatically saves the process's context. So we're already half done. We just need to decide who gets the processor next and switch to their context. But if we're on a single processor, a whole bunch of stuff gets really simple. Which is why in the OS class we have a single core operating system, because I don't want people's lives to be even more miserable. It's hard enough. Okay. So multi-core systems obviously complicate the situation immensely. Any questions about stop or suspend? Okay. Let's see. Resuming. So we have to resume a suspended process because we really only schedule processes that are in the ready state. That's kind of the rule. When something is in the ready state, what we're saying is it could proceed if it had a processor to run on. If it's not in the ready state and it's not running, then what we're saying is we really don't want to schedule this for one of a variety of reasons. If it's a blocked state, then it's because we're waiting for something that's slow. If it's suspended, then we're saying, I just don't want to schedule it right now. So one of those situations prevents us from scheduling it. So if it's ready, we could schedule it, and if not, then we don't. So basically when we resume, we basically have to move it into an appropriate state. So like I say here, it's either in the ready suspended or block suspended state. If it's ready suspended, it's super simple. We just drop it back into the ready state. Put it into the ready queue. The scheduler may pick it. It may pick something else. If it's in block suspended, then we just change it to block because the process is still stopped for other reasons. Okay? So this resume operation is very simple. You notice if the status is ready suspended, we just change it to ready and we schedule, which means, hey, scheduler, pick somebody to run. We have no guarantee that it will be P. Make that really clear. P may be really low priority. There may be something really important that needs to be taken care of. P may be the only process. So in that case, it may get the processor right away. Okay? Otherwise, if we're in block suspended, we go to blocked. Okay? So those are all pretty straightforward. Last thing, destroy. So we can call this on a running process. Let's say if it calls exit or gets a seg fault and you're not handling them, which you generally do not. So in that case, basically we need to invoke the scheduler. So the other thing, of course, is that processes have state. They have resources, so we need to do cleanup. And so that's probably the most important part of cleaning, destroying the process. Okay, so these are all the things that destroy has to take care of. If we're currently running, then we need to stop the process and tell the scheduler, hey, we're pulling this off the CPU, so the CPU is available for something else. And then we go through and clean up all the resources the process holds. This may or may not involve actually doing things like deleting files or closing files, depending on how many processes have files open and so forth. Then we release the process control block, and if we needed to schedule something, then we go ahead and invoke the scheduler. Oh yeah, and the ... in here is really important as well, because remember, we have init, we have zombies, we have that kind of stuff we need to take care of. So if we have child processes, we need to assign them to whoever the orphanage is in the operating system. Maybe it's init, maybe it's somebody else, but we have to send all those things over so that the operating system can take care of these orphaned child processes. Okay, any questions on this? There's one thing that I was thinking was interesting to mention, but it slipped my mind. I can't think of it. I guess we'll go on. Yeah, I still really can't think of it. Okay. Let's see. Now obviously there's a lot of details here left out. Probably the most important one is how we move from blocked into ready. And we talk about that pretty early on in the operating system class because of how important it is. Remember how I was mentioning in maybe it was last lecture, how we basically in the operating system keep track of every single thing that processes could become blocked on. And we typically do it at the device level, not the file level. So we'll have a device like disk 1, disk 2, the network card, the terminal, and there'll be a queue for each one of those things. So if a process gets blocked, we want to keep track of what that thing is blocked on so that when that device signals, we can easily go and look at the processes that care about the device, and then we can figure out if any of those processes should wake up now. Okay, so that allows us to go from block to ready easily. Okay, so we don't talk about that very much. But the other question, which we're going to start talking about next, is what do we do with the ready processes? How do we figure out who should go next? And I mentioned that the scheduler is responsible for this. So we have a set of ready processes, and I've sort of been calling it the ready queue, but it frequently is not a queue. Anybody familiar with the current Linux scheduler, the Linux process scheduler? Anybody know what it's called? Like this much? Yeah. This much familiar? Do you remember what it's called? Well, they've been switching it for like the last 3 kernel versions, so it's kind of funny. Linux is great because being that it's not owned by a corporation, they have a lot of freedom to try stuff. And the current scheduler, I believe, is called the Completely Fair Scheduler, which is like the best name ever. Very politically astute name to give it. Before that, it was the Order 1 Scheduler, and then before that, they actually used another scheduling mechanism that we'll be talking about, I think, next time we talk about it. But anyway, so frequently we don't have a queue. We have some other data structure. The completely fair scheduler uses a tree. And the order one scheduler, I think that, it used a whole bunch of queues, if I remember correctly. It had a really interesting mechanism. So anyway, but the scheduler has this problem of, I've got a set of processes that could have the CPU. Which one do I choose? And you might say, why in the world would this be a complicated choice to make anyway? But if you think about it, if you have this general purpose system that's supposed to do everything well, then it is a challenging problem because programs can have very different behaviors. Does anybody here like Emacs? I don't know what the kids use these days. A couple people use Emacs. VI, does anybody use VI? Vim, I know it's Vim. I run Vim.
Well, unfortunately, if you type VI, then it doesn't autocomplete to Vim, it just does VI.
Oh, that really sucks then. We need to fix that. That sucks. What about other editors? Anybody use Xcode? No, what do you guys use? Sublime, okay. Does anybody else? Anything else? I mean? Oh. All right. So we have these various editors that we're using. Emacs / whatever you like. GCC / Clang to implement, to actually compile it. So we're running that at the same time. Obviously, that's not going to take a lot of time to compile. So let's say that maybe you're compiling the Linux kernel in the background for funsies. I don't know if people do that anymore. VLC / QuickTime / whatever, your favorite video player, because you're like, I don't understand this assignment. I need to watch Donnie's lecture on it. And for I don't know why, but you're running also a program to compute the next Mersenne prime. Maybe you want to make history. So anyway, you have these 4 programs. Do they all have the same scheduling considerations? The obvious answer is no, but I mean that's also because I'm asking the question. The answer probably no. But yeah.
Because some of them have latency requirements.
Some have latency requirements. So let's say that I switch over to let me try to think of a different way of putting it. My Mersenne prime program wants to output some text to the console. Is it critical that that thing outputs it within 1/10 of a second or within 3 seconds? Does it really care? Do we care? And the answer is pretty much not. Does VLC, or does anybody know what VLC is? That's the, good, I hope so, open source video player, or QuickTime, does that have scheduling requirements as to when it does stuff? Yes, like very much yes. Please, please, yes. I don't want my video to stutter because that would mean my computer is slow and I need to upgrade it or something. So you can see VLC has very important time scheduling constraints. What about Emacs? What is Emacs going to be doing most of the time?
Receiving interrupts.
No, in fact. Let's say wall clock time. Like if you're talking about its time on the CPU, you're correct. But let's say wall clock time. What is Emacs mostly going to be doing?
Nothing.
Everybody see that? It's going to be blocked on console because it's like the user is thinking a lot right now and they're not typing at all, which is probably a good sign because you should think before you type, right? It's bad if you don't. So, but you can see that we have different constraints here. GCC is probably the most interesting one because it's going to have different phases of its behavior. Initially, it's going to do a whole bunch of I.O. Then it's going to do a whole bunch of thinking. And then it's going to do some more I.O. And then guess what? More thinking. And so forth. Okay, so GCC is probably the most interesting one because its behavior is going to change over time. So process scheduling considerations. Well, the answer is yes. So these are just some of the things that we talked about. You type on Emacs, it should respond quickly. You want it to respond very fast. I don't know if any of you have had that experience where you are connected to a remote computer, you're typing, and like it takes 2 or 3 seconds for the data to show up. Oh, it's so annoying. I was uploading a lecture recording from home and at the same time trying to SSH into some other place. And it was horrible. It was like type, 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 type. And then like 30 seconds later, it pops up. Yeah, it's just terrible. Nobody wants to use a computer that behaves that way. GCC and Mersenne prime. They shouldn't screw up the video playback. That would be really helpful. And the prime number generator, we kind of don't care. We know it's going to take hours and hours and hours. So we really don't want it to impede the other programs at all. So these are just some examples of how we'd like the operating system to behave, and a good OS will do that. A good scheduler will do that. A bad scheduler will have this all mixed up so that you type into Emacs and your video playback stops being nice. The Mercine Prime program is screwing everything up. Okay, you can imagine ways that bad schedulers would affect this situation. So processes do vary widely. We have general categories or behavioral patterns that we describe these as. We have compute-intensive processes, which basically just want to sit on the processor and talk to memory and do computations with the ALUs. That's all we care about. The examples that I have here are horrible examples. Database servers do a lot of I.O., in fact. So they try to do as little I.O. as possible, but they still do a lot of I.O. So they do have phases where they're very compute intensive, but a lot of times they actually are I.O. intensive. Same thing with compilers. So I guess maybe some of the time they fit in the compute intensive. A much better example would be MATLAB, Mathematica, okay? Your Mercine Prime computation. Let's see. Interactive processes. So interactive processes are at the other end of the spectrum. They're always waiting for input from somewhere, typically from the console because they're interacting with the user. Okay? And so what happens is they're almost always not in the ready state. They're almost always not on the processor because they're blocked on stuff. But that moment that input comes in, they should get the processor immediately because you want, for the sanity of the user, to let the computer program respond to the user very quickly. Okay, so interactive processes are a very interesting thing where they're almost always blocked, but when they're unblocked, they should respond immediately. So they should get the processor right away. And then you have real-time processes, which are even worse because they basically say, I don't need a lot of time on the processor, but I absolutely need it on this schedule. I need to have it now, and then I need it again in 20 milliseconds, and then I need it again in 20 milliseconds. I don't know, what, 20 milliseconds? That works out to what, 50 frames per second?
16.6.
Yeah, so if we want, we have to think about exactly what frame rate, or if we're playing audio, what audio rate we need for these kinds of things. But we have deadlines, or else people get unhappy. Now, does anybody know, because we don't really talk about real-time processes until next lecture, does anybody know the difference between hard real-time and soft real-time? Anybody come across that before?
Does it have to do with like writing to buffers as opposed to writing directly to
No. It's more of a conceptual thing, interestingly. Hard real-time means if I miss a deadline, the system has failed, and it must stop. That's hard real-time. Yeah, and soft real-time is, I didn't get around to drawing the next frame of the kitten video when I wanted to, but that's okay, life will go on. Okay, there's a slight tiny, no! So, that's like, the video stutters or it just plays back a little bit slower. Okay, so that's soft real-time versus hard real-time. A great example of a hard real-time system would be the software that controls the giant robotic arms with welding things on the end on the auto assembly line. Because something is telling the robotic arm, hey, go right here and make a weld. And there sure as hell better be a car right where that thing wants to make a weld, or else you have a problem. So that's a good example of a hard real-time system. Okay? Even when you make phone calls, you'd like the phone, you'd like the call to be connected within a certain time frame. That's not a hard real-time system either. It's like, because, okay, the call fell through, or I got tired of waiting and hung up. I don't know if you've noticed, but if you ever had your cell phone and you call a landline you're sitting right next to, you hear it ring, and then a few seconds later it starts ringing on the phone. Well, that's variable. Okay, that's soft real time. Okay, so interesting variations. I don't really need to spend that much time talking about it, but why not? The other thing, scheduler should be fair. What does it mean for a scheduler to be fair? Well, really what we're saying is that no process should ever have the situation where it will never get the processor. Every process should eventually get some time on the CPU. We're not saying that they all get the same amount. We may play favorites, but we should give everybody a slice of time on the processor. Everybody should progress. Finally, the scheduler needs to be fast. And this is where we start saying, hey, I want a pony too. Because basically, anytime that I'm spending scheduling, I'm not spending running programs. And if my scheduler takes like 3 seconds to decide who to run, I've got a really crappy scheduler. Okay? That's a terrible situation. Okay? So I need to have an answer fast. And so you'll notice that a lot of these scheduling algorithms are written to come up with an answer fast. Okay? Now, like I say, your context switches take 5 to 10 microseconds, which does correspond to several thousand instructions. I'll go through the details of that next time. That's sort of one of the things that I get really frustrated. People think context switches are free. People think processes and threads are free. They're so totally not. So we'll spend a little bit of time talking about that next time. We want to avoid context switches if we can. The more time we spend context switching, the less time we spend running programs. So you can see that somewhere in that 5 to 10 microseconds, there should be a little call to the scheduler to figure out who to go next. Okay? That's kind of the upshot of this. So what does the scheduler have available to it as far as information is concerned? Okay. Well, it's part of the operating system, so it can watch what the program does. It can know when I/O is being performed. How does it know that? What? Oh, okay, you have to trap into the kernel to do I/O. So the kernel knows, right? The kernel's always aware of what's going on because you have to go through the kernel to get I/O. Okay. How quickly will I/O requests be satisfied? Well, you can find that out as well. And it's interesting, but if you think about doing FTP or HTTP data transfers or BitTorrent or whatever the current flavor is, when you're doing that, if you are consistently calling into the network code, then the OS can say, hey, you keep making that call and it keeps coming back relatively quickly. So you're doing some kind of regular I/O interactions and they are satisfied this quickly. Or you're doing regular I/O interactions and it's poor Caltech student trying to think of things to write in their humanities paper and they wander off and do something more fun. And now the program is waiting for a long time and the kernel can say, hey, these I/O requests are taking a really long time to satisfy. So the kernel can look at that stuff and figure it out. Also, does a process have real-time requirements? Well, we'll talk about that in a second. Yes?
Is this why if you go in your kernel for a long time and you sit back down, the first little thing that might sometimes do, and then it'll get back up to you?
There's another reason for that. The answer for that is virtual memory, but we haven't talked about virtual memory yet. We will talk about it, though. Yeah, it's so I'm so excited. So, it's cool stuff. All right, so the things that we can't know. There's certain things we can't know. What's going to happen in the future? We have no idea. Okay? Which is why, I mentioned this before, the best scheduling policies are called clairvoyant policies. Because they mean that you know the future. And of course, the reason why we even care, it's like, why would you even care about that kind of thing? Well, the answer is, you can always compare a real-world policy to the clairvoyant policy by recording the program's behavior and then checking how the clairvoyant policy would behave. And then you can say, this comes within 10% of being able to predict the future perfectly. Or this comes within 5% of being able to predict the future. So it is a useful concept, but you kind of need to know all of history to be able to figure out if a particular policy is good or not. So anyway, we can't know these things with certainty in the future, how long a program will take to block an I/O or how long it'll take to complete. But interestingly, we can make observations and make predictions about some of these things. So we use past behavior to predict future behavior. And it's okay. It works pretty well. And does a process block regularly or does it get preempted regularly by the kernel? So we make an assumption, which is generally an okay assumption, that the future will be like the past. So if a program is blocking a lot, it will continue to block a lot. If we have a program that blocks a lot, but it resumes a lot because its resource becomes available quickly, then we can notice that as well. And if we have programs that are sitting on the CPU and get preempted a lot because the kernel's timer goes off and it's like, oh, you're still on the CPU. I see how you're behaving. Then we notice that kind of stuff. Okay? And so we have a model. And it's simple because it has to be updated quickly, and we can't do a huge number of, we can't data mine or anything stupid like that because it's a schedule. Okay? The other thing about this is that it also needs to be able to adapt to changing program behaviors. Think about MATLAB and Mathematica. So for a period of time, it's interactive because I'm typing stuff. And then I decide to start running something, and it switches from being interactive to compute intensive, and it does computations for a while. And then it changes back to being interactive. So our scheduler's model needs to be able to move as well from one behavior to another. So we have these kinds of constraints that our scheduler needs to satisfy. There are some things that we can't guess. I suppose you could try. It'd be very interesting to try, but typically it's completely unsatisfactory for an operating system to try to guess that something's a real-time process. Okay? So in those situations, we have to tell, the program tends to tell the kernel, I am a real-time process and I need scheduling time on this interval. Okay? So I have an example call here for Linux, how a program can say, hey, I'm a real-time process and I have these scheduling needs. And what's really neat about it is the operating system can actually tell the process, no, sorry. We talk about that more in the operating system class, but there's certain real-time scheduling algorithms where you can say, you know what, if I accept this process, I'm overcommitting the CPU. And then you can actually say, sorry process, something else is going to have to terminate before I allow you to be a real-time process. Okay? So it's kind of an interesting thing. Let's see, also, you can set the priority of a process. So now the user can tell the operating system, you know what, it just really isn't that critical to me that I find out the next Mersenne prime right away. So you can go in and set the process's priority. And that will affect maybe the size of the time slice or the maximum priority level in the scheduler that you are granted. Okay. So has anybody used nice before? So you can make programs nice or not nice when they run, and that'll affect its scheduling. Basically what it means is the program will be preempted more frequently when somebody else wants to run. Okay. It will still get plenty of CPU time, but it won't. Oh, that was the thing that I wanted to mention with destroy. What does your computer do when you have no processes to run?
Keep checking for processes.
Where? How?
Probably just a scheduler and like some sort of sleep interrupt.
Kind of. But the way that it's a really interesting, the way that the kernel does is it has an idle process. And the idle process will run. That'll be the thing that's selected if nothing else. It's kind of one of these general, let's make it generalized so we don't have special cases. So there's an idle process that basically sits and waits for other processes to come along. So it's very friendly. It always yields.
Okay. So is it just like a while one yield?
Something along those lines, yeah. So it's a very interesting thing. It's sort of the nicest process you can imagine. And it's supplied by the operating system because the CPU needs to do something. I think on multi-core operating systems you can be more clever and have them halt the processor and then restart it so that you actually save power, that kind of stuff. But yeah, there's some really interesting little techniques if you have nobody to run. Okay, let's see. Next thing. So round-robin scheduling. We'll talk about a few scheduling algorithms, try to get through these. It's fun to talk about. So round-robin scheduling is a very simple approach. We're basically going to pick some time slice, and here I've said 1/10 of a second. And what we do is we just go through all of the processes that are currently running and give each process that chunk of time. If it blocks, it forfeits its entire time slice. Okay, so if I'm Emacs and I am waiting for a character, then I just stop. Okay? If I'm a compute-intensive process, I get to use the whole time slice. Even if people start typing, who cares? I get the whole thing. Okay? Yeah. So it is fair. Yay, it's fair, I guess. And it's very simple, so it's easy to implement. In fact, this is kind of what you guys do for assignment 6. Compute-intensive tasks love this scheduler because they never get interrupted by anybody else. Remember, if I'm spending time context switching, I'm spending time not computing. And so compute-intensive processes love this because they get a nice large chunk of time where they are guaranteed the processor. And they can use it until their time slices up and they get preempted. Interactive tasks hate this scheduling approach. Because basically it is going to be forfeiting most of the time that it has on the processor always. because it's always going to be blocking. And furthermore, if there are compute-intensive tasks on the system, well, when that resource becomes available, it's going to have to wait many processes worth of this time slice size to actually handle the I/O. So the interactive processes are not able to preempt other processes to handle their I/O quickly. So if you had this kind of scheduler on your system, you'd be like, why is it not being very responsive? Okay? It would not be responsive at all because round-robin scheduling is very simplistic. Okay? Now you can implement prioritization by just changing the size of the time slice that you give. So for example, what you could do is give compute-intensive tasks a smaller time slice and real-time processes a larger time slice. I mean, not real-time, interactive processes. Now, probably that's not going to do any benefit except just make compute-intensive tasks take longer because that larger time slice is not going to be useful to an interactive process. It's going to do just a little bit of computation and then yield the rest of the time. So really all you're doing is making the time slice size smaller, and you're making your compute-intensive tasks take longer because you have more context switches during the lifetime of that program. Okay. Any questions about this? You can see that it's simple. Not very cool, though. We don't like it too much. So yeah, interactive tasks are going to be delayed by long-running processes. So another thing that we could do is we could look at how long does the program typically run before it's blocked or preempted. Okay? So like I say, we can use the past behavior to estimate the amount of time that it'll take before it's blocked. And so what we do is we come up with another scheduling approach called shortest jobs first. And again, this is based on a guess, but let's pretend that our guesses are good for now. And so what we do is anything that's really short, we say is the highest priority. Anything that we know is going to take a long time is lower in priority. And so presumably, interactive processes will now be happy because they're always going to be the shortest job. They'll always get to run first. So what we're doing here is we're optimizing for response time. And you'll notice that from the time that a process is able to run to the time that the process gets the CPU is minimized by shortest job first scheduling. So let's say we had 4 jobs with estimated lengths 1, 2, 4, and 8. These are our shortest jobs. You'll notice that our first process is always happy. Response time is 0. Okay? And then we have 1, 3, and 7. Basically the sum of the time that it takes to get to running that job. And just to illustrate, if we schedule these in the opposite order, the order that compute-intensive processes would want, and no human being would want to use a computer, then you can see how the average response time goes way up when we have largest jobs running first. So shortest jobs first does optimize for response time. So interactive processes love shortest job first scheduling. But then we have an issue. What if new jobs keep showing up? Yeah, so we have this interesting issue that if we just keep adding them into the queue and they keep being shorter than other stuff, they're going to jump ahead. And so we may have stuff toward the back that maybe never actually gets the processor. So you say your previous example, we had 1, 2, 4, and 8. At time step 5, something else shows up. And so we go ahead and finish the current job. Now technically, if we wanted to preempt, we have an interesting thing here. Because the red job is 4 cycles, but we already completed 2 of them. So the new job doesn't preempt the current job because we have an estimate that it's still going to take 2 cycles. So it's like, why interrupt that? So then we start the new job, and you can see that the long guy is really sad. He gets pushed back. So what would happen if this kept happening? Is this a fair scheduler? Not as stated. Okay. Problems, yes. We have problems, yes. If we keep having short jobs arrive, it's going to push the long jobs back in the priority order, and they'll never get a chance to run on the processor. Okay. So this is a good example of an unfair scheduling algorithm. Now, it's pretty easy to tune this so that it is fair. Okay. A very simple approach is we always put stuff we have some point of time in which we just allow longer jobs to go forward. I don't know. You could come up with some clever way of doing that. You could probably the most interesting way would be to combine somehow the time we added it to the queue plus the estimated amount of time it will take. And use that so that long jobs eventually trickle up to the front. Yeah, something like Reddit. So we could do something like that, and that would be the most interesting thing to do, and that would make it more fair. But you can see that what happens is the response times go down, or I should say they go up. We don't want them. This is a situation where up is worse, like golf scores. Okay, so the average response time goes up, so we're not happy, but at least the compute-intensive task will eventually get a slice on the processor. Okay. So we have these two interesting scheduling algorithms. We'll talk about a third one next time, and it's still not going to be the whole gamut of algorithms. It's really cool. But we have round robin, which compute-intensive tasks love, interactive processes hate. And we have shortest jobs first, which interactive processes love and compute-intensive tasks hate. So can we combine them? Remember we talked about combining specific solutions into a more general purpose, elegant solution. We'll talk about that next time. Also, we'll have a little bit of discussion of real-time tasks because that's also very important. Okay, any questions? All right, we'll see you